In this tutorial, we'll cover the basic principles to chemistry, including stoichiometry. When working with chemical problems, you need to start with a reaction form, which can either be written as an unbalanced reaction or a balanced reaction. Unbalanced reactions are written only to show the major reactants and products for a reaction. In this example, you have calcium hydroxide, which is referred to as lime by its common name, reacts with a strong acid, hydrochloric acid, to yield calcium chloride. You can see that this reaction ignores the conservation of mass because oxygen is present as a reactant and is not shown as a product. This is not technically possible. A balanced reaction reflects the conservation of mass for each constituent and expresses the quantitative relationship. For instance, the same chemical reaction written in a balanced form shows lime reacting with hydrochloric acid to yield calcium chloride and water. A balanced chemical reaction shows the principle of conservation of mass. In this form, you will see that 1 mole of calcium is present as a reactant and 1 mole of calcium is present as a product. You will also see that 2 moles of chlorine are present as a reactant and 2 moles of chlorine are present as a product. You could go through each element and see that the number of moles starting equals the number of moles finishing. It is very important that you always start with a balanced chemical reaction. You should also be very fast at reading a chemical reaction such that you can interpret this balanced reaction as 1 mole of calcium hydroxide reacts with 2 moles hydrochloric acid to yield 1 mole calcium chloride and 2 moles of water. You should also be able to read in this reaction that the chemical reaction goes to completion. This is represented by an arrow that is one direction. Later in this lesson plan, we will work with reactions that are at equilibrium. Once you learn how to read a balanced reaction, you should be able to convert mass concentrations of reactants to mass concentrations of secondary reactants or products. In this example, it is asked, how many milligrams of hydrochloric acid are needed to neutralize a 1 liter solution of 50 milligrams per liter of calcium hydroxide? We want to find the milligram of hydrochloric acid per liter. The steps for this are to first convert mass concentrations to molar concentrations. It is not meaningful to discuss the milligrams of a calcium hydroxide reacting to the milligrams hydrochloric acid. 1 mole of calcium hydroxide reacts with 2 moles of hydrochloric acid. You should think of this as a molecule reacting to a molecule. The milligrams, or the mass of that molecule, is nonsensical in that discussion. So the first step is to make this conversion. We do this simply by multiplying the milligrams per liter calcium hydroxide by the molecular weight. So if we do the molecular weight of calcium hydroxide, you should be able to solve this as 74 grams per mole. That would also equal 74 milligrams per millimole. We bring that down and we see 74 milligrams per millimole equals 0.675 millimoles of calcium hydroxide per liter. The second step is to use stoichiometry to relate millimoles calcium hydroxide to millimoles of hydrochloric acid. So 0.675 millimoles of calcium hydroxide per liter. And from the chemical reaction, we see that 2 millimoles of HCl react per 1 millimole of CaOH2. And so we're left with 1.35 millimoles of hydrochloric acid per liter. The final step is to convert millimoles HCl to milligrams HCl. The molecular weight of hydrochloric acid is equal to 36 grams per mole, or 36 milligrams per millimole. So coming down, we see that 1.35 millimoles per liter HCl times 36 milligrams per millimole yields 48.6 milligrams of hydrochloric acid per liter. Here we have two balanced chemical reactions. In the top, the reaction goes to completion because hydrochloric acid is a strong acid. When working with a reaction such as this, it is very straightforward to use a stoichiometric relationship such as 2 moles HCl per mole of calcium hydroxide, as we did in the previous example. In the second chemical reaction, though, we see that the reaction is bidirectional. In this case, it would be difficult to make a straight stoichiometric relationship. Instead, we typically assume equilibrium and write a mathematical expression to solve for concentrations from that. That will be the next module.